Thanks, Jingyi, for the introduction. So this talk is about dichotomy theorems for exact counting graph homomorphisms. So in the talk, I will cover some of the dichotomy theorems for counting graph homomorphisms, and then I will try to show you some segments of the proofs, some for the algorithmic part and some for the harness part, with the goal to demonstrate some of the commonly used techniques in this area. Now, these results are not very recent. I think the nearest one is already 5 years ago. Still remember the summer I spent at Madison with Jingyi and Pingyang. But that was already 5 years ago. So I apologize in advance if some of the parts of the talk you've already seen them before. But hopefully this would refresh your memory about these dichotomy theorems. So you probably heard about the word dichotomy a lot from Jingyi's talk yesterday. Dichotomy theorem, a complexity dichotomy, would be a theorem that classifies the complexity of a collection of problems, not just one single problem, but hopefully a collection as big as possible. And usually such a theorem would involve a so-called tractability criterion. It's a condition on the problem definition. And usually the theorem says that if your problem satisfies this condition, then it's easy to solve. Otherwise, you can show that it's hard. So one of the classical results in this direction is Schaeffers' dichotomy theorem. It's for decision version of CSP over the Boolean domain. Okay, I will not define CSP. I think many of you are familiar with CSP because this is not the focus of the talk today. I will define them more formally in tomorrow's talk. But there is this Feder and Body's conjecture that this dichotomy should hold for CSP for any language over any finite domain. For any such language, the conjecture says that the decision problem is either in P or NP complete. And the best we have right now is the dichotomy theorem for domain size 3. But this talk is about counting problems. So here are some classical counting problems like counting vertex covers, counting colorings, counting satisfying assignments, counting perfect matchings. Now this one may not be familiar to some of you. It's given a graph and you count the number of induced subgraphs with an odd number of edges. But we'll see later, like this problem actually played, I would say, a pivotal role in the sequence of dichotomy theorems that we'll see in a few slides. So there are three well-studied frameworks for counting problems or collections and more general counting problems. There are these counting graph homomorphisms, which we'll talk about today, counting constraint satisfaction problems. I'll talk about them tomorrow. And there are these Holland problems Jingyi and Han well talked about. So let's start with the definition of graph homomorphisms. Given two graphs, undirected graphs, so for this talk, whenever a graph comes up, it's undirected. So given two undirected graphs, homomorphism is from G to H is just a map from the vertex set of G to the vertex set of H, with the property that every edge of G is mapped to an edge of H. And graph homomorphisms were first studied by Lovász, and I think this is one of the theorems he proved about graph homomorphisms. And actually in the theorem, the number of homomorphisms played an important role. So the theorem says that take any two graphs, H and H prime. They are isomorphic if and only if you take any other graph G and the number of homomorphisms from G to H and from G to H prime are exactly the same. If they are isomorphic, then these two numbers should always be the same for any G, but it's an if and only if thing. Now, the first work on graph homomorphisms, dichotomies for graph homomorphisms is this dichotomy theorem by Hale and Neshatriel. And the decision version of the problem is also called edge coloring. So edge is the graph. So you take any edge, fix any graph edge. That's the graph you map to. And the problem is to decide, given a graph, input graph G, whether there exists a homomorphism from G to edge. So every fixed graph edge would define you a problem, and that's the class of problems that we're interested in here. And Hale and Neshatriel proved that every such problem is either in polynomial time or NP complete. Now we're interested in the counting version. So let's just give the notation, which we'll see again and again in this talk. So given a fixed graph edge, I'm going to use eval edge to denote the following problem. The input is the graph G, edge is fixed, and we're interested in computing the number of homomorphisms from G to edge. So again, every fixed graph edge would give you a problem, and we have this dichotomy theorem by Dyer and Greenhill, which says that for any edge, this problem is either solvable in polynomial time or Schaeffers complete. And here is the tractability criterion. Basically, the tractable cases are graphs in which every connected component is either an isolated vertex or a complete graph with all the self-loops, or complete bipartite graphs. So these are the only tractable cases, and if your graph does not fall into one of these cases, then it's intractable, it's Schaeffers complete.
Sorry, so complete bipartite graph, so if you take complete bipartite graph with self-loops,
yes.
It's Schaeffers.
No, that's easy. That's in P. So solvable in polynomial time if every connected component is one of these three graphs, three types of graphs. So by complete graph with self-loops, I just mean if you look at the adjacency matrix, it's all one. That corresponds to a tractable case, and you can take the disjoint union of such graphs that's still tractable, that's still solvable in polynomial time. So we can then see that vertex covers and colorings, decolorings can be both expressed as eval edge, counting graph homomorphisms for some small graph edge. For example, for vertex covers, edge is just a graph with two vertices and these two edges, one edge between them and one self-loop. So it's clearly a graph that violates the tractability criterion, so we know by the dichotomy theorem that this is Schaeffers complete. And the same for decoloring, because the graph should be the complete graph with no self-loops. And by the dichotomy theorem, it's also Schaeffers complete. Now for this problem I mentioned earlier, counting subgraphs with an odd number of edges, it's not clear how you can express this problem using as eval edge for some graph, fixed graph edge. But it turns out that you can express it by generalizing this counting problem to graph homomorphisms with weights. Okay. So more generally, given any symmetric matrix A, we use eval A to denote the following problem. So A is a symmetric matrix, and for now, let's assume that entries of A can take the most general complex values. So take any graph G and an assignment C that assign values or indices of the matrix A to vertices of V. Each such assignment defines an H weight on each H, A CU and CV. And if you take the product over all H's, that's what we call the weight of the assignment, of this assignment. And the sum that we're interested in is this sum, let's call it Z sub A of G, over a sum of weights over all possible assignments. So if you spell it out, it's this sum of products here. Now the connection between this problem and the counting graph homomorphism problem is that when you take A to be the adjacency matrix, the 0, 1 adjacency matrix of the graph H, then these are essentially the same, exactly the same problem, because this weight is 1 if and only if all these edges of G are mapped to edges of H, and 0 otherwise. So these two problems are exactly the same. And this function Z sub A is also called partition functions in statistical physics, and I'll actually call them partition functions in the rest of the talk. Now back to this example, counting induced subgraphs with an odd number of edges. It turns out that this problem is equivalent to computing the partition function with this matrix A, 1, 1, 1, minus 1, this 2 by 2 very simple Hadamard matrix. And here is the connection. If you take any assignment of V and think about the graph induced by vertices that are assigned 2, the weight is minus 1 if and only if this graph has an odd number of edges, right? Because only edges in this subgraph get the weight minus 1. All other edges get weight 1. Okay. And the weight is 1 otherwise. Now using this observation plus another observation that the total number of assignments is exactly 2 to the number of vertices, these two problems are equivalent. If I know how to solve this one, then I can easily count subgraphs with an odd number of edges. And in general, if you allow weights like roots of unity, then we would get interesting matrices like this. And we want to know how difficult these matrices are. And just a heads up that it turns out that all these matrices are tractable, and we'll see how what's the algorithm behind all these tractable cases in a few slides. So here omega is the third root of unity, zeta is the fifth root of unity, and these two are the so-called Fourier matrices, 3 by 3 and 5 by 5 Fourier matrices, which I'll define in a few slides. But the point is that all these three matrices, together with this 2 by 2 matrices, they all correspond to tractable cases. So after the dichotomy of Dyer and Greenhill for counting graph homomorphisms, or equivalently for 0-1 matrices, we have this dichotomy theorem by Bulatov and Grove in 2005. It's the same statement, but now for non-negative, symmetric non-negative matrices. So one thing I would like to point out is here I'm using R sub A to denote the set of algebraic real numbers, just to make sure that we're fine with the representation of numbers. As long as you take any reasonable computational model for algebraic numbers, this theorem would hold. But in this talk, don't worry about algebraic numbers or their representations. Just take it as real numbers. And this is the tractability criterion of their theorem. It's probably the most natural generalization of the dichotomy criterion of Dyer and Greenhill. It says that A gives us a polynomial time case if and only if A is, first of all, a block diagonal matrix, and every block is either a rank 1 matrix or has this form. So 2 by 2 matrix, the diagonals are zeros, and the 1, 2 block is rank 1 matrix. So these are all the tractable cases. If your matrix does not look like this, then it's Sharpie hard. And I said this kind of generalized Dyer and Greenhill because full rank 1 matrix is like a complete graph with self loops, and this matrix would just seem very similar to complete bipartite graphs. But now you can put rank 1 matrices there instead of all 1 matrices. But describe the similarity, I would just emphasize like this theorem has really, really a lot of applications, and it's just very easy to apply it. And actually, all the hardness proofs I'll talk about today and tomorrow are reductions to this dichotomy theorem. And the reason why it's so easy to apply is the following observation. If I have a non-negative matrix and I'm interested in its complexity, then all I need to do is to look at its 2x2 submatrices. If I'm able to identify a 2x2 submatrix of this bigger matrix, which has, let's say, at least 3 positive entries, but is not rank 1, then I can just apply this theorem and claim that it's sharply hard. Okay, so all you need is to, if you want to prove this matrix is hard, just try to identify a 2x2 matrix, which has 3 positive entries, but not rank 1. Okay. And recently there was a new exposition by Grove and 30 with a few shortcuts in the proof for this dichotomy theorem. Now, after non-active matrices, it's just natural to move on to real or complex weights. And once you move to real or complex weights, you got cancellations. This monster of cancellations show up. Now, cancellations sometimes lead to very efficient algorithms, such as algorithms for determinants and holographic algorithms by Valiant in 2004. So in general, cancellations would give you more tractable cases, which turns out to be the case, as we'll see in a few slides. This somehow makes the proof of a dichotomy more difficult because intuitively the boundary between the tractable and intractable cases become more complicated, and it's just becomes more difficult to figure out where exactly it becomes tractable. But dichotomy theorems arise, and we have first in 2009 this dichotomy theorem by Goldberg, Grove, Juren, and 30, which shows that for any non-active real and symmetric matrix, the problem is either computable in polynomial time or sharply hard. And then it was generalized by Jingyi, myself, and Pingyan to all the complex matrices, symmetric and complex matrices. Now, I will not be able to state the tractability criterion for either of these two papers because it's actually much more involved than, for example, the criterion of Bulatov and Grove. I think if I want to state it formally, I need at least like 10 slides for that purpose. But roughly speaking, tractable matrices corresponds to certain rank 1 modifications of tensor products of those Fourier matrices you saw before, which I'll define in a few slides. And I would like to just point out that these 3 words, rank 1 modifications, actually has a lot of work hidden behind these 3 words. So we've covered all the theorems, and here is the plan for the rest of the talk. First of all, I want to show you the algorithmic ingredients of these dichotomy theorems. I will show you, what are the algorithms that were used to solve those tractable cases. Then I'll give you a segment of the hardness proof. We'll give a self-contained proof. And the hope is that I can use this proof to demonstrate 2 elementary but also commonly used techniques in all these works called building graph gadgets to do reductions and also interpolations. So let's start with the algorithms. And just as a warm-up, let's look at rank 1 matrices. And let's show that rank 1 matrices, the partition function is really easy to compute. So A is a rank 1 matrix, which means there exists a vector B such that you can write Aij as Bi times Bj. This is the partition function that we want to compute. Now, the first thing I did here is just to replace the assignment by a sequence of variables where xi denotes the value assigned to vertex number I. And here we plug in this expression. Then the next observation is this product, you can actually write it as a product over i's. And each factor is b sub xi to the power of the degree of vertex I in the graph. So this now becomes a product of things over i's, over the vertices. And it's easy to rewrite it as a product of sums. But now each of these sums are very easy to compute because remember the matrix A is the fixed constant. So the size of the matrices, M is a fixed constant. We can afford to sum up M things here and then take the product. A similar algorithm would work also for such 2 by 2 matrices with the rank 1 matrix B. And the next thing is also easy if you have 2 matrices that are both easy to solve and you take the direct sum of these 2 matrices, then it should also give you a matrix that is easy to solve. So first of all, it's without loss of generality to assume that the graph we're interested in is connected, because if you have a graph with multiple connected components, then the partition function of this graph is just the product of the partition function over the product of the connected components. So if G is connected, then it's easy to show that all the assignments C's that have non-zero weights are basically those map all the vertices to the first block, or the assignments that map all the vertices to the second block. So we can write the partition function as the sum of the partition function over using A1 and the partition function using A2. So if both A1 and A2 are easy to solve, A is also easy to solve. Okay. And what we've done so far is basically we covered all the tractable cases in Bulatov and Grove dichotomy theorem. Okay. So with 2 slides, we proved like half of the theorem. Even though I would say the hardest part of that theorem is like 100 times more difficult than, but at least statement-wise, this is half of it. Okay. Now, the next thing is, what about this matrix 1, 1, 1, minus 1? I think it has been open for some time. Like we don't know whether this is easy or hard. But then there is this really nice observation made in Goldberg, Grove et al., Grove, Jeren, and 30, that if you index the rows and columns of this matrix by 0, 1 or Z2, then you actually have this very nice expression. The xy's entry is just the minus 1 to the power of x times 1. Right, the only chance you get a minus 1 is both x and y are 1. And using this observation, we can plug it in the partition function, and we get this expression, where we have a sum over a bunch of variables over Z2. And each term is a power of minus 1, so it's either 1 or minus 1. And in the exponent, we have a quadratic polynomial of x1 through xn. And it turns out that such sums are easy to compute. They can be computed in polynomial time, and I think this is known. I don't know which paper gives this result the first, but it's definitely in this book by Liddell and Niederreiter in about finite fields. So it said that if you take any quadratic polynomial, and the sum is computable in polynomial time in n, the number of variables. Now, combining this theorem together with this observation, this connection, we know that the partition function of this matrix is easy to solve. And the same holds for this 4x4 Hadamard matrix, which takes a little bit work because you have to try and see that if you index the rows and columns by Z2, so let's say you index the rows by 0, 0, 0, 1, 1, 0, 1, 1, then you can express the entries as minus 1 to the power of x1, y2 plus x2, y1. And using the same argument would reduce us to the algorithm behind this theorem. And it turns out that this theorem can be generalized to work for any q, any integer q, not just for 2, not just for prime numbers or prime powers. It can be extended to any integer q. So given q and quadratic polynomial over zq, this sum can be computed in polynomial time. Okay, so minus 1 is replaced by a q's root of unity, and the exponent is again a quadratic polynomial over x1 through xn. And it can be computed in polynomial time even if q is given as part of the input, so encoded in binary, and even if we're not given the prime factorization of q. Now, once we have this algorithm, immediately we know that all the Fourier matrices are tractable. So here is the definition of the Fourier matrices, an m by m Fourier matrices. The entries satisfy this expression. The xy's entry is just the m's root of unity to the power of x times 1. So these are Fourier matrices, and by this theorem, we know that all of them correspond to tractable cases. Also, we can take tensor products of any of these matrices. I'm not going to do that, but just some calculation. If you have a tensor product, then you can write the partition function as the product of partition function using the two matrices separately. So this, roughly speaking, covered most of the tractable cases in the real and complex graph homomorphisms or partition functions. Remember, I said earlier that most of the tractable cases are tensor products of Fourier matrices, and now we know they're all tractable. So before moving on to the hardness part, I just want to show you this cute and very short, very, very short proof for the q equals 2 case. Because, the idea generalizes to any q, but with more work. So the proof basically just has two cases. In the first case, we have quadratic term xi squared. In the other case, every term is a cross term xi, xj, I not equal to j. Sorry, I think this is the case when we only have cross terms. Then we write the polynomial in terms of x1. In this way, then L is affine linear form, and f prime is a quadratic polynomial. Then in the sum, let's sum over x2 through xn first, and then x1. And it turns out that this sum over x1 only depends on the value of L. L depends on x2 through xn. And it's 2 if L equals 0 and 0 otherwise. So this clearly simplifies the sum to be this one, where we no longer have x1, but has this condition that L should equal 0. But this can be also removed by a replacement of variable. And this would reduce the sum into a new sum, but now with n minus 2 variables. Just keep doing this each round. Either you already know each round you would get a new factor of 2 here, and after, let's say, n minus 1 rounds, you can just do it brute force. The other case is exactly the same, except I think these two rows get switched. So the condition is that L should be equals 1, but everything else is the same. So this finishes the proof of the theorem that any such sum, given any quadratic polynomial, it's easy to compute. Now for this general theorem, I want to point out that at the high level it's similar. Each round we just find a way to reduce the sum to a kind of smaller sum. But now there are two cases. Either we can similarly reduce the number of variables by at least 1, or we sometimes need to reduce the size of Q. And the other thing is, when we're interested in the case when Q is given in binary, not fixed but as part of the input, then Gauss sums play a really important building block of the algorithm. The reason being that even if x1, even if, let's say, I only have one single variable, x1, I cannot afford to brute force take the sum, because it has Q many terms. And Q is part of the input, so Q is exponentially large. But when that happens, it actually is closely related to Gauss sums. You can use Gauss sum, the expression behind Gauss sum, to compute it exactly and efficiently. So these are everything about algorithms. Next, I will show you a segment of the hardness proof, and it's called the group condition lemma. Okay. So here is the definition. Let A be a symmetric M by M matrix. We say it's a discrete M discrete unitary, capital M discrete unitary. If, first of all, every entry Aij is M's power of unity. And also the first row is all 1. And because it's symmetric, the first column is also all 1. And also, you take any two rows, they are orthogonal, meaning that their inner product is 0, and here is the definition of the inner product. This means the complex conjugate. So if you have a matrix satisfies all these conditions, we say it's a discrete unitary. And here is the so-called group condition lemma. It basically says that if you have a matrix, which we already know it is discrete unitary for some integer m, then either this matrix should satisfy the group condition, which I'll define next, or you can already show that the problem is Schaeffers. If it violates the group condition, then you can already show that the problem is a Schaeffers. And here is the group condition. It says that you can take basically any two rows of the matrix. Here, I and j could be the same. And take the Hadamard product, entry-wise multiplication of these two vectors. You get a new vector. And the condition says that this new vector should also be a row vector in this matrix. And the reason why it's called group condition is that if it satisfies this condition, then the rows under the Hadamard product would be a group. That's why it's called a group condition. And the lemma basically tried to show that every discrete unitary matrix is either satisfy the group condition, or we can already show it's Schaeffers. Before proving this, here is the motivation why we want such a lemma. The observation is that these Fourier matrices, they're not only discrete unitary, they are discrete unitary, but they also satisfy the group condition. And if you take any two rows here, do the Hadamard product, it would still give you a row in this column. A row in this matrix. And the next lemma says that basically these are all the discrete unitary matrices that satisfy the group condition. So every discrete unitary matrix that satisfies the group condition must be the tensor product of Fourier and so-called generalized Fourier matrices. I don't think it's important here. But these are basically the 4x4 Hadamard matrices you saw earlier. Those are called generalized Fourier matrices. But forget about this for now. It tells us that once you get a matrix that is discrete unitary and satisfy the group condition, it's a tensor product of Fourier matrices. And all these matrices we have seen in the algorithmic part that they're all tractable. So once you have a discrete unitary matrix, once you already know the matrix is discrete unitary, we get a dichotomy theorem because either it violates the group condition, for which this lemma tells us that it's Schaeffers, or it satisfies both conditions, discrete unitary and group condition, then this lemma tells us it's actually one of the matrices that we know how to solve efficiently. And the group condition was first introduced in a paper by Goldberg et al. For +1, -1 matrices, and then it was generalized to all the complex valued matrices or the roots of unity stated earlier. Okay. So I have, I think, about 12, 13 slides for the proof of this lemma, but here is the high-level sketch. So I have this matrix A that is discrete unitary. What we'll do is to construct a sequence of non-active and symmetric matrices. Let's call them B bracket P for every integer P, positive integer P. And we're going to show that all these matrices, each of these matrices, the problem of computing the partition function can be polynomial time reducible to the problem defined by A. Then we move on to show that one of these two cases happen. Either one of these matrices give us a Schaeffers problem, and this is done by invoking the dichotomy theorem of Bulatov and Grove. We just look at these matrices closely and try to apply this their dichotomy criterion and see if we can show that one of them is violates the criterion and it's Schaeffers. If we can do that, this polynomial time reduction would also tell us that the problem defined by A is Schaeffers. On the other hand, if we cannot show this, or every matrix B bracket P satisfies the criterion of Bulatov and Grove, we're going to use this as a really, really strong property to show that A satisfies the group condition. And the first part, where we construct these matrices and give these reductions, is the place where we use graph gadgets. And in the second part, where we show either this or this happens, is the place where we use interpolations. So this is the first gadget. A graph gadget is just a graph, but now with two special vertices called U and V. I highlight them in red here. And then you can add as many vertices you want and as many edges as you want. Here in this picture, I use a blue thick edge to denote m-1 parallel edges. And just a reminder that m is the parameter in the unitary matrices. And here is the second gadget. You start with the first gadget, but now make a copy of C and D. So now we call them C1, D1 and C2, D2. Then just make a copy of all these edges between C1, D1 and U, A, B, V and put them here. So we always have one copy of A and B, but when P goes up, we have more and more pairs. And the P gadget has C1, D1, C2, D2, up to CP and DP. So this is how we construct the P gadget for every integer, positive integer P. how we use these gadgets, given the graph, say G, we can replace every of its H by, let's say, the piece gadget. So here we first remove that H and then identify the two special vertices of the gadget with the two vertices of this H. So here I basically replace the H by the first gadget. And you do this for every H. Okay, you pick a P and you replace every H by the piece gadget, and we call the new graph we get G bracket P. And it turns out that there is a symmetric matrix B bracket P. We'll derive its entries on the next slide, but there is such a matrix which has the same size as A, but satisfies this expression. If you take the partition function of G using B bracket P, it's the same as the partition function of the new graph G bracket P, but now using A. And such an equation would give us automatically a polynomial time reduction from matrix B bracket P to A, because whenever I have a graph G that comes in and I want to compute this, I can just do this replacement, get a new graph G bracket P, and ask for the partition of G bracket P under A. It's not go. It's only this way. Now, what is the entries of B bracket P? If you plug in, all the definition of the partition function and the construction of B bracket P, the ijth entry of B bracket P is the following. You assign value I to this special vertex U, assign J to this special vertex V. They are fixed. They receive values I and J respectively. And then you allow the rest of vertices to take all possible values, and you take the sum of weights over all such assignments. That would give you the ijth entry of B bracket P. And the B bracket P we get in this way would satisfy the equation and has the polynomial time reduction to A. So for example, this is for B bracket 1. It's ijth entry. Everything just by definition, but I only want to point out that we have these conjugates here because, for example, we have the conjugate of A sub BD, because between B and D we have not just one H, but capital M minus 1 H's. And because we know that all these numbers are M's roots of unity, taking the M minus 1's power is exactly the same as taking the conjugate. Okay, that's how we get all these 4 conjugates here. They correspond to the 4 blue H's in the picture. Now, it's clear that every H is incident to either C or D, so we can write it as the product of 2 sums, 1 over C and 1 over D. And just stare at them for 5 seconds, you will figure out that these two are conjugate of each other. Okay. So it's exactly the norm of this sum, but squared. Okay. So what we have here is a closed expression for the ijth entry of the first matrix, where we have a sum over all possible pairs of A and B. And then we have this sum and take its norm and square it. And similarly, we can do matrix B bracket 2. And it turns out that the only difference is that the exponent here is now 4 instead of 2. That's the only difference. And in general, for the piece matrix, everything is the same except that the power is now 2p. And for convenience, let's just rewrite this sum as this inner product, where we first take the Hadamard product of the ith row and the conjugate of the jth row. And then we take the product of the ath row and the conjugate of the bth row, and then do the inner product. After that, we take the norm and raise it to the 2p's power, and we sum over all possible values of A and B. Now it's a fairly complicated expression, but the first observation is that it should be clear that it's non-negative. Let's forget about positive, but it should be non-negative because it's a sum of norms. It's positive because if you set A to be I and B to be J, then these two are exactly the same vector. And we're taking the inner product of the same vector, so we would get something positive. We would get M, or M to the 2p. So every entry is actually not only non-negative, but positive. It's also symmetric. Now it's not straightforward from this expression, because in this expression, AI and AJ are not the same. Like we have a conjugate on AJ, but it's not surprising because if you go back and look at the gadget is symmetric on U and V. And also, I mean, this IJ is equal to Ji because, you know, we have this sum over all possible A and B here. So these are symmetric and positive matrices. It's like the best place to apply the dichotomy theorem of Bulatov and Grove. But before that, let's take a closer look at the diagonal entries, I equals j. Once I equals j, the first vector just becomes the all one vector. Basically just disappeared. And then this becomes the inner product of A's row and the B's row. And this expression, we know exactly what it is, because the matrix is supposed to be unitary, discrete unitary. So every inner product here is either 0 if A is not equal to B, or M if A equals B. And if you go through all possible pairs of A and B, we have exactly M pairs where this inner product give us M. So it gives us M to the 2p plus 1. Okay, so we know exactly what the diagonal entries are. Now we can apply the dichotomy of Bulatov and Grove. So what we have here, we have a positive matrix. Every entry is positive, and we know exactly its diagonal entries. They're all the same. Then the only chance that this matrix survives, Bulatov and Grove is that the whole matrix has the same value. Every entry is M to the 2p plus 1. If the matrix doesn't look like this, we already know it's Schaeffers. And because we have a reduction to A, this also tells us that A is Schaeffers, then we're done. This is the first case of the theorem, and we're done. So the only case left is that actually these matrices, each of the matrix has the same entries. Every entry is equal to M to the 2p plus 1. And in this case, we'll use this to show that A satisfies the group condition. And this is a place where we use interpolations. So fix a pair I and J, I not equal to J, fix a pair. And let's say we're interested in the B bracket P, the IJ century. And it has this expression. Now, let's use the following notation. So X sub ij is the set of all possible values of this, the norm of this inner product, by taking A and B to be all possible values. And for each possible value in X sub ij, Sij bracket X tells us the number of pairs AB such that this is equal to X. Now once we have this notation here, we can rewrite this sum as the sum over Xij, and Sij bracket X times X to the 2p. Just plug in the notation here. Now, of course, we have no idea what Xij contains, what other possible values this can take. But at least we know it can be 0, and it also can be M. To get m, you can just plug in set a equals I and b equals j, and this would equal to m. To get 0, you can plug in a equals, I think, I and b something different from j. Then you would get 0. So even though I don't know what exactly they're in x sub ij, I know 0 and m are two of its elements. And it turns out this is enough for us to figure out what exactly xij is. Because let's take these equations for p from 1 to the size of xij minus 1. These are all the equations we need. We don't need equations for larger p. Plus this equation that if you sum over Sij, it should be equal to m squared because we have exactly m squared many pairs of AB. And these expressions together form a Van Mont system. It's a linear equation system, and the coefficient matrix is a Van der Mont matrix, and it should have a unique solution. But we know that it has this solution. The solution is set Sij bracket m to be m. There are m pairs that give us m, and m squared minus m pairs give us 0. If we plug these two equations back into these equations, they will hold. So this should be the only solution. And we can conclude that Xij not only just contains 0 and m, it's exactly 0 and m. So we're almost done because we have shown something really nice, that if you take Aij, Ab to be any value and look at this norm, it should be either 0 or m. It cannot take any other value. Okay. We're already very close to the group condition. To prove the group condition, let's fix I and b. So let's say I want to prove that the ith row and the b's row, if you take the Hadamard product, it's another row in the matrix. So let's fix I and b. We set j to be 1, so this becomes the all-one vector. Then we have that this sum, this norm is either 0 or m. But on the other hand, because it's a discrete unitary matrix, I know all these rows together form an orthogonal basis. We can just use Pascal to show that this sum should equal to exactly m squared. This is because these vectors all have, all of their entries are roots of unity, so all these entries are roots of unity, so I know exactly what its norm is. So here is something strange, like I know that each of these terms here should be either 0 or m squared. But I also know they sum to m squared. So the only chance is that there is exactly, there exists an A such that this equals m. And we're done because we have two vectors, their inner product has norm m. On the other hand, we know that all these vectors, they share the same first entry, right? Their first entries are always 1. Remember, in the condition, we require that the first row and the first column are all 1. So we have two vectors, their inner product is m, has norm m. They share the same first entry, both are 1. The only chance you can satisfy this is that they are actually the same vector. Okay, which tells us that if you take the Hadamard product of the ith row and the b's row, you would get the a's row of the matrix, which is exactly the group condition. Take the Hadamard product of any two vectors, row vectors, you get another row vector of the matrix. So this finishes the proof of the group condition. And I just want to conclude that what we covered today, we covered most of the algorithm ingredients of these dichotomy theorems, and we covered this segment of the proof called the group condition lemma, where we demonstrated these techniques called graph gadgets and interpolations. And these are widely used in this area. Sometimes all you need is to take these techniques to an extreme. For example, sometimes you need not just one layer of interpolations, but multi-layers. And sometimes you need to design crazy graph gadgets such as this one. So the plan for tomorrow is I will spend most of the time on the dichotomy for unweighted CSP. So I will cover the tractability criterion and the techniques used in this dichotomy, like multi polymorphisms and witness functions, and also the main counting algorithm. Then I'll try to try to generalize it to non-active and complex CSPs. So thanks.
Any questions? Yeah, so in the tractable sum, we have -1 when Q is 2, right? But when Q is 2, you can also use I with some restriction on the quadratic function.
What do you mean? I see. So you can, yeah.
Yeah.
So I don't know how that's related to
like a even number, like in general even number. What would happen?
Right. So you're saying, what if it's -1, but the polynomial is not over Z2, but is the polynomial over?
No, I mean the base
Z2?
is I, but the polynomial has like a crossing term has to be even coefficient.
Right.
Then it's also tractable, right?
Yeah, I think it can be also solved using the theorem, but you need to build a connection between
Yeah,
the.
but my question is like how to generalize for general Q.
I think if it's like 2 to the, for example, if Q is something like a power of 2, you should be able to do some generalization there. And actually, in our proof, the most difficult case is when Q is like a power of 2. Q is odd, it's actually much simpler than the case when it's a power of 2. And I think that the reason behind it is exactly what you said, like when you have a power of 2 and when you have coefficients that are even, there are interesting thing, like more interesting thing going on there compared to like the odd case.
2 is an odd prime. It's actually in the paper. Any other questions?